Now, the first two we saw for B1 and B2, we now have a B1, sorry, we have B1 squared, B2 squared. Here we don't have them squared, so we'll just square both sides just so we can plug these in more nicely. More nicely. Sure. B1 squared, B2 squared is equal to A1 to the fourth, V squared over C to the fourth. And that's going to be equal to A1 squared minus 1 over C squared times A1 squared V squared over C squared plus 1. And if I multiply, let's get rid of our fractions here. So I'm basically going to multiply everything by C to the fourth. Yeah. I want to make sure I'm not. Yeah. Sometimes when I'm doing the long derivations, I do a step and then later I have to undo it. So that was what I was checking just then. And so we end up with A1 to the fourth V squared is equal to, well, that C squared will cancel out with two of those. So it's A1 minus 1 times, then the C squared left to multiply through, I get A1 squared V squared plus C squared. So in essence, by C to the fourth, I split it in half, multiply that by C squared, and multiply that by C squared. And I want to distribute it out. Yes, I do. Let's go ahead and multiply this, multiplying binomials. New voice. How do you multiply binomials?
You distribute.
Okay. So on the left-hand side, I'll A to the fourth V squared. All right. Oh, that should be A1 squared. Did you want to keep going?
Not really.
All right, someone else?
Foil.
Okay.
So A1 to the power 4, then B squared, right?
All right, there's first.
A1 squared, C squared.
Okay.
Negative C squared.
Oh, do it the last, okay.
Yeah, and then negative A1 squared, C squared.
Okay. Conveniently, that term cancels out. Ultimately, I'm solving for A1, because that's an unknown there. So let's solve for A1 here. So let's get the A1 terms together and everything else on the other side. So I get C squared over on the left-hand side. And I'm left with A1 squared C squared minus A1 squared V squared. What does A1 squared equal?
C squared over V squared.
1 minus C squared.
If you factor out the A1 squared, you have
Okay.
C squared minus V squared.
So A1 squared, C squared minus V squared.
And then you divide both sides by C squared minus V squared.
All right, so then we get C squared over C squared minus V squared. We actually have seen this before, but
Don't those C squared cancel out, or? Oh.
no. But let's take that step. Let's multiply top and bottom by 1 over C squared. So I get 1 on top, and on the bottom I get 1 minus v squared over c squared. Yeah, we can't just cancel out like that.
Oh,
And,
That's beta.
pardon?
That's beta. V squared over C squared?
Yep, so that's 1 over 1 minus beta squared. And that's a1 squared, so let's take the square root. So a1 is equal to, technically, plus or minus the square root of 1 over 1 minus beta squared. And what is this?
Gamma.
Yes. So what is gamma? So we now have our relationship here, at least one of them, because we started out with x prime is equal to a1x plus a2t, and then that became a1x minus vt, and so now it's equal to plus or minus gamma x minus vt. And the question is it the positive or the negative? Well, if I have some event going on over here, it's positive for x and x prime. So the people in the car and the people standing on the side of the road both have this in the positive direction. And so therefore this has to be a positive number here. It's going to be positive. I will spare you from the solving the time one. But we do have, this is known as Lorentz transformation. That if I'm relating what's happening in two different reference frames, in other words, a moving frame and a still frame, or two moving frames, I know that the position in the second frame, in the moving frame, at least based on our drawing right here, is equal to gamma times x minus vt. We'll be using this in just a moment. And then t prime, if you actually, we went through that, this would be gamma times t minus v over c squared x. And let me double, I want to confirm that one. Yep. And recognize that x and the x's are when they're moving in the same direction as when they're in the, try that again. X prime and x and these are when the moving frame is moving in the x direction. If we're perpendicular to that, if I have something that's moving this way right here, well, there's no dilation going on in that direction, and so y prime is equal to y, z prime is equal to z. And that's going to come in a moment. All right, so let's actually use this. Let's go back to the, I'm going to do pole and barn instead of car and garage, just because my notes are pole and barn, and this stuff is confusing enough without having to be able to check. Questions on any of this before we actually look at the sort of the big object into smaller object? We'll take a small break after we do just one little bit. All right, so 16-meter pole into 10-meter barn. Barn. Pole. All right, so this person's running at the barn and wants to get the entire pole inside the barn. And just adding to it, just to give a sort of visual image. As soon as the pole was completely inside the barn from the point of view where it can fit, the left door will close. So we'll have the left door closes. And eventually, if it'd be hard to stop, the pole's going to go through the right side. But and let's have the traveling. I was trying to remember whether we solve for speed or whether we're just, I'm giving it to you. So beta is 0.866. So if beta is 0.866, what is gamma?
$1.9998.
Which we'll just round off to. And let's see, which one are we going to make the prime frame? So this will be the prime frame. Unprimed. We have x1, t1. 0 meters, 0 seconds. This is when the left door closes. So as soon as the left end of the pole is inside the barn, the left door closes. X2, T2. This is 10 meters, 0 seconds. Right door closes. Because from the person in the barn's point of view, the pole is shrinking. The pole gets smaller. And so both doors will be closed at the exact same time. And then X3, T3. This is when right end of pole hits the right door. So that event happens at 10 meters because, again, from the, not clear, this is where x equals 0, x is equal to 10 meters. Now, how much time takes place? Well, how big is the pole when it enters the barn? If it's traveling at 0.866 times the speed of light, how long is the pole from the barn's point of view?
10 meters?
No. No, it's not, unlike the car problem, the car and garage problem, the pole was, because they gave you the speed, the pole is shorter in the barn frame than the size of the barn. We're dealing with length contraction. What's the proper length?
16 meters.
Yeah. So we have LP is equal to gamma times L. 16 is equal to 2 times L.
Length is 8.
Yeah. So this guy's cruising along at 86% the speed of light, and then there's going to be that moment when if the pole is completely inside, it is 8 meters long from the barn's point of view. How much distance is left to go?
2 meters.
So if you're traveling at 0.866 times the speed of light and you have 2 meters to travel, how long is it going to take? Well, I know speed is distance over time. So 0.866 times the speed of light, which is about 3 times 10 to the 8 meters per second, is equal to 2 meters over time. How much time does it take? I will agree with that. I think we can narrow it down a little bit better than that.
7.7 times 10 negative 9 seconds.
In other words, 7.7 nanoseconds. This will make these all nanoseconds. All right. So this pole's traveling really fast. It does fit, from the barn's point of view, it does fit completely in. Both doors close at that moment, and then 7.7 nanoseconds after it comes in, it smashes through the right side. So, let's do it from the pole's point of view. Because from the pole's point of view, the barn's coming at it, so the barn is shrinking. But we know about simultaneity. We know that when the doors close, just because they close at the same time from the barn's point of view doesn't mean they close at the same time from the pole's point of view. So, I have the formulas over there. X prime is equal to X, gamma X minus VT. So, if I'm looking at the first event right here, when the left door closes, that is 2 times 0 minus 0.866 C times 0, which would be 0. So they at least both agree on that one. T prime is equal to gamma times T minus V over C squared times X. Well, that's 0. That's 0. So T prime.
Yeah, 0.
All right. So this is barn's point of view, and so from the pole's point of view, X1 prime, T1 prime is equal to 0 meters, 0 nanoseconds. They synchronize there so that they both start the watch at the same time. All right, event number 2, when the right door closes. Time is still 0 there, but X is not, X is 10.
Troy.
Yep. And the time That's 2 times 0 minus 0.866 c over c squared times 10.
C's the speed of light, correct?
Yes.
What was that value again?
About 3 times 10 to the 8th.
Oh, gotcha. Thank you.
I have it up. Wait.
Right there, yep. I'm confused.
.77 times 10 to the negative 8.
Seconds, which would put it at negative 57.7 nanoseconds. It is negative, but minus there. X2 prime, T2 prime is 20 meters, negative 57.7 nanoseconds. And then crashing the pole through. Let's do it down here, plug it into that equation right here. So for x3, it's 2 times x, which is 10 meters, minus v, 0.866 times the speed of light, times time, which is 7. Oh, I guess plug it into the formula here. So this would be 7.7 times 10 to the negative 9. Using that time right there in that position. And see, it's still 3 times 10 to the 8.